In this video, we'll be going over how to use the rule of 72 and how to prove that to double your initial investment and to prove that your initial investment depends more on your APR and the times of compounding rather than your initial investment itself. So to start out, we'll do a quick recap on what we learned in our last video. In our last video, we stated that P is our principal or our initial investment, R is our APR or our annual percentage rate, N is the number of compounds per year, and T is equal to our number of years. So now, to start out proving that our initial investment doesn't actually affect our doubling time as much as our actual percentage rate and number of compounds, we're going to do a quick example. In our example, we will be taking the main equation, which is compounds per year. So the equation we used last time, which is A equals P parentheses 1 plus R over N to the power of N times T, or NT. So here, we'll just make up some values for this example. So we can say that P equals 3,000, and we can try it from there. And we'll do one more, which is going to be P equals 5,000. Okay. Now, we are going to substitute everything into this equation. I'll give all the information now. So we have 3,000 as our initial investment, which is P. We have our percentage rate as being, let's just say, 2.5%. 2.5%. And it's going to be compounded, let's just say 12 times a year, so monthly. Okay. And we're going to do the same thing for this. But here you can see our p-value has increased by quite a significant number of $2,000. We're going to have the same everything, 2.5%, and 12 times in a year, which is basically monthly. And now we're just subbing into this equation. We're going to do what we did last video really quickly. So we have A equals 3,000 parentheses 1 plus 2.5 has to be in a decimal for our R value. So 2.5 divided by 100, and 2.5 divided by 100 is just 0.025. That's divided by our times we're compounding per year. In this scenario, we said 12. So we're doing 12. And then it's to the power of N times T. Our N was 12. 12 times our time. In this scenario, we're just going to say time is going to be unknown because we're going to solve for our doubling time. So we have 12 times T, right? And we want to find our doubling time, right? And so doubling time is going to be 2 times our initial investment. So we have 6,000 equals 3,000 parentheses 1 plus 0.025 over 12 to the power of 12t. We're solving for t. Best way I think is to do this is use Mathway or Nspire or a calculator. Solve for x, and x is just going to be t. It's going to be the variable you're solving for. So in this scenario, we're going to input this equation because we substitute all our values in. We're just solving for this variable t. And that variable is what's going to be our answer for this type of question where they're looking for the doubling time. Scenario t is going to be equal to 27.75 years. And I personally just like to round up, so we can just say t equals 28 years. Around 28 years. Then we're going to do the same thing, but we said our initial investment is going to be 5,000 because we're trying to prove that our initial investment does not affect our doubling time as much as our actual percentage rate and compoundings per year. So we're going to do the same thing. So we have A equals 5,000 parentheses 1 plus 0.025 over 12 to the power of 12 times t. We're going to do the same thing. Put this into our calculator, solve for t. Here we got t equals 28. And for this one, we're looking for our doubling time again. And in order to do that, we're going to set this equation set to 10,000 because 5,000 doubled is 10,000. So we have 10,000 equals 5,000 parentheses 1 plus 0.025 over 12 to the power of 12t. And we get t equals, and surprisingly, we also get t equals 27.75 and t equals 28 years. It's not that surprising, since we are actually trying to prove that our initial investment doesn't affect our doubling time as much as our APR and our compoundings per year, and that's just been proven right here. We've seen that we invested $3,000 our first time, and we had a doubling time of about 28 years. And then here we invested $2,000 more dollars, $5,000. Everything else was the same, and it took the same amount of time. That's what they're trying to prove, that your initial investment does not affect your doubling time at all, almost. Now, we are going to write one more. This is going to prove the doubling time is affected by APR and annual compoundings per year, or times and is going to prove that your doubling time is going to be affected by your APR and your compoundings per year. So now we're going to do 3,000. So we have 3,000 as our P, right? And we have A equals 3,000, parentheses 1, plus, we're going to double our APR. So now, since we doubled our APR, so we have 5%, and 5% is just 0.0. And 5% is just 1 over 20, which is 0.05 over, and we're going to increase our compoundings per year to 365, so daily compounding, so 365. And we're going to put it to 365 times t. Again, we're looking for doubling time, so we're going to double 3,000, so we get 6,000 equals 3,000, parentheses 1 plus 0.05 over 365, parentheses 365t. Right, I'm going to solve for t one more time. And in this scenario, we get t equals 13.86, or about t equals 14 years. So now you can see the dramatic change. It basically got cut in half by doubling our APR from 2.5 to 5%. And that is what we have just proven, that APR and compoundings have a greater effect than your actual initial investment. Now we're going to check our findings by using the rule of 72. The rule of 72. The rule of 72 states that 72 divided by your interest rate equals your doubling time. So t in this scenario is your doubling time, and this is going to be a rate. Now, what we're going to do is we're going to substitute our values we just used and prove again what we found using the rule of 72. And a quick thing to note is when you're using the rule of 72, your rate is going to be the whole, right? So if it's 5%, it's going to be 5%. Whereas when we were doing R here, we took the decimal form. In this scenario, we're going to have the whole number. So it's 5, it's going to be 72 divided by 5, and we're going to find our actual doubling time. So now let's start with our initial finding, our initial equation, which we did, which was P equals 3,000, and our interest rate was 2.5. So we have 72 divided by 2.5 is going to equal our doubling time. 72 divided by 2.5 is about 28.8. So that's going to be our doubling time with an interest rate of 2.5%. Now we're going to do the same thing. We're going to do 72 divided by 5, because in this second one we had an interest rate of 5%. Everything else stayed the same. Our compounds were increased. We're just looking for doubling time, so we're just going to be using our interest. That's all the equation is asking for. So we have 72 divided by 5. 72 divided by 5 is about 14.4 years. And you can see it's exactly half, right? 28.8 divided by 2 is equal to 14.4. And we found the same thing to occur in this one as well. We had 14 here, and we had 28 here. 28 divided by 2 is equal to 14. So both ways, we've just proven that our annual interest rate and our compoundings affect our doubling time more than our actual initial investment. I hope this video really helped, and if you believe it did help, please consider to like and subscribe. Thank you so much.